Have you ever looked up at the stars and felt a sense of awe, wondering if there's more to the universe than just vast, silent emptiness? What if that darkness isn't empty at all, but filled with hints, patterns, and even messages waiting to be understood? The great physicist Sir James Jeans once said something that still echoes through the halls of science today. The universe appears to have been designed by a pure mathematician. That idea might sound like science fiction, but what if it's closer to the truth than we've ever dared to imagine? In this video, we're going to explore 24 astonishing anomalies, evidence gathered from the edges of cosmology, quantum physics, and mathematics, that suggest space is not just an empty stage for matter and energy. Instead, it may be intelligently encoded, woven with precision, purpose, and something that looks remarkably like a grand design. We'll journey from the mind-bending fine-tuning of the universe's fundamental constants to mysterious signals from deep space, from the large-scale architecture of galaxy clusters to the intimate connection between consciousness and reality itself. Each anomaly invites us to reconsider what we think we know about existence, pushing the boundaries of science, philosophy, and wonder. By the time we reach the end, you won't just see the night sky differently, you might begin to see everything differently. This isn't about providing easy answers. It's about asking bigger questions, igniting curiosity, and exploring the possibility that the cosmos is far more mysterious, more intentional, and more astonishing than we've been taught. So settle in, open your mind, and join me on this journey. Let's dive deep into the clues that suggest our universe is not a cold, empty void but a cosmic masterpiece, rich with intelligence. For thousands of years, when our ancestors looked up at the night sky, they saw a vast and silent void punctuated by pinpricks of light. To them, space was the ultimate emptiness, a dark canvas upon which they projected their myths, gods, and fears. The ancient Greeks envisioned a series of crystalline spheres, while early navigators used the stars as a fixed guide in an otherwise mysterious and impenetrable abyss. This view of the cosmos as a cold, empty expanse persisted for centuries, a backdrop to human drama that was beautiful to observe but fundamentally unknowable. But what if that perception was merely a limitation of our perspective? What if, with every technological leap and intellectual revolution, we began to peel back the layers of that darkness to discover it was never empty at all? The shift began in earnest with the invention of the telescope. When Galileo first turned his rudimentary spyglass toward the heavens, he didn't just see more stars, he saw mountains on the moon, moons orbiting Jupiter, and a universe that was suddenly dynamic and detailed. This was the first crack in the idea of a static, empty void. Then came Isaac Newton, who gave us the laws of gravity and motion, suggesting that space itself was a stage governed by precise mathematical rules. The universe was no longer a chaotic mystery. It was an orderly system that could be understood, measured, and predicted. Yet, even then, space was still largely seen as an empty container, a passive arena where celestial objects simply played out their parts. The real transformation in our understanding started in the 20th century, a period of unprecedented upheaval in physics. Albert Einstein's theory of relativity completely revolutionized our concept of space and time. He proposed that space isn't just nothingness, it's a flexible, dynamic fabric that can be warped by mass and energy. Imagine space as a taut rubber sheet. Place a heavy bowling ball in the center, and it creates a deep well, causing nearby marbles to spiral inward. This isn't just a metaphor, it's how gravity works. Einstein showed us that the cosmos has a structure, a geometry that can be bent and shaped. Emptiness suddenly had properties. it could ripple, carrying gravitational waves across billions of light years from colliding black holes. At the same time, quantum mechanics was revealing a universe that gets even stranger the smaller you go. Scientists discovered that what we perceive as a vacuum is not empty. Far from it, at the quantum level, space is a seething, bubbling foam of virtual particles popping in and out of existence in a frantic dance. Empty space, it turns out, has energy, a fundamental tension known as vacuum energy. This means that the void is actually teeming with potentiality and fluctuation. It's alive with activity. This discovery alone challenges the very definition of emptiness and suggests a cosmos that is fundamentally active and full of information. A pivotal moment in this journey was the accidental discovery of the cosmic microwave background radiation in 1965. Arno Penzias and Robert Wilson, two radio astronomers, were troubleshooting persistent static in a giant microwave antenna. After eliminating every possible cause, including famously evicting a pair of pigeons, they realized the noise was coming from everywhere in the sky. It was the faint afterglow of the Big Bang, the cooled remnant of the universe's fiery birth. This wasn't just leftover heat, it was a snapshot of the infant cosmos, a message from the very beginning of time. This discovery provided overwhelming evidence for the Big Bang theory and showed us that the universe has a history, a story written into the very fabric of space itself. This historical arc, from a silent abyss to a structured, dynamic, and information-rich cosmos, sets the stage for everything that follows. It shows that our quest to understand these anomalies isn't wild speculation. It is the next logical step in a long tradition of empirical curiosity and philosophical wonder. We are following in the footsteps of the great thinkers, using the tools of science to ask age-old questions. Are the mathematical patterns we see in nature just convenient descriptions, or are they evidence of a deeper code? Does the universe's apparent fine-tuning suggest a designer, or a multiverse, or something even more profound? This rich tapestry of cosmic mystery is what will continue to unravel, starting with the first and perhaps most compelling anomaly of all. Now let's take a closer look at this first and perhaps most profound anomaly. Consider the force of gravity for a moment. It feels so solid, so immutable, holding us to the ground and keeping the planets in their orbits. But what if it were just a tiny bit stronger, not by a lot but by as little as 1 part in 10,000 trillion? In that universe, stars would burn through their nuclear fuel at a terrifying rate. A star like our Sun, which has shone steadily for billions of years, would instead flare up and burn out in less than a single year. There would be no time for planets to cool, for life to emerge, or for intelligence to evolve. The cosmos would be a fleeting spectacle of brilliant, short-lived furnaces. Or let's examine the strong nuclear force, the glue that holds the very nuclei of atoms together. If this force were even slightly weaker, it couldn't overcome the repulsive force between positively charged protons. Simple hydrogen would be the only element that could exist. There would be no carbon, no oxygen, no iron, none of the building blocks essential for planets, oceans, or living organisms. The universe would be a boring, inert sea of hydrogen gas. Conversely, if the strong force were just a bit stronger, it would bind protons and neutrons so tightly that all the hydrogen in the early universe would have fused into heavier elements. Without hydrogen, the fuel for stars, the cosmos would be dark and starless. The balance required for a universe that can create complexity is unbelievably precise. This isn't just about 1 or 2 constants, it's a symphony of precise values. The speed of light sets the ultimate speed limit for causality and determines how energy and mass relate. The cosmological constant, which governs the energy density of empty space and the acceleration of the universe's expansion, is fine-tuned to an almost incomprehensible degree. Physicist Lawrence Krauss has calculated that if this value were marginally larger, the universe would have expanded so rapidly that galaxies and stars could never have formed. If it were slightly smaller, the cosmos would have collapsed back in on itself in a catastrophic Big Crunch, almost immediately after the Big Bang. The margin for error is vanishingly small, like hitting a bullseye on a dartboard that is the size of the observable universe. This remarkable balance is what scientists call the anthropic principle. In its simplest form, it states that we can only observe a universe that has the conditions necessary for our existence as observers. It seems like a tautology, but it points to a deep mystery. Why is the universe so hospitable? Why do these fundamental numbers line up in just the right way to allow for galaxies, stars, planets, and life? For some, like physicist Paul Davies, this goes beyond mere coincidence. He argues that the impression of design is overwhelming. The laws of physics appear to be not just a random set of rules, but a carefully crafted recipe that makes the universe not only possible but fruitful. This precise calibration suggests something far more profound than random chance. It hints at a cosmos that was, in some sense, set up with intention. It's as if the laws of physics were dialed into specific values from the very beginning, creating a universe capable of generating complexity and, ultimately, consciousness. This doesn't necessarily point to a traditional, bearded deity in the sky, but it does force us to confront the possibility of a deep, underlying intelligence, a cosmic architect who wrote the initial code. The fine-tuning of physical constants stands as the first and most powerful clue that the emptiness of space is not empty at all, but rather encoded with the fingerprints of a grand and purposeful design. But if the fine-tuning of physical constants set the stage for a life-friendly universe, the next anomaly offers us a snapshot of its very first moments, a baby picture of the cosmos that is anything but smooth and featureless. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, trying to eliminate a persistent, frustrating hiss from a massive horn-shaped antenna. They scrubbed out pigeon droppings, checked every connection, and pointed the antenna in every possible direction, but the noise remained, a constant, faint microwave signal coming from everywhere in the sky at once. They had accidentally stumbled upon the cosmic microwave background radiation, the cooled remnant of the universe's fiery birth in the Big Bang. This discovery was monumental, earning them a Nobel Prize and providing the strongest evidence yet for the origin of our universe. But this afterglow held a deeper secret that would only be revealed with more sensitive instruments. The initial assumption was that this background radiation would be almost perfectly uniform, a smooth echo of a hot, dense, and featureless early universe. But as technology advanced, satellites like NASA Cosmic Background Explorer, or COBE, began to map this radiation with incredible precision. What they found was astonishing. Instead of a featureless blanket of microwaves, the sky was painted with tiny, intricate fluctuations, minuscule variations in temperature, on the order of 100,000th of a degree. These are the anisotropies, the seeds of all future structure in the universe. It was as if we had discovered the cosmic blueprint. These tiny ripples were the gravitational wells that would eventually, over billions of years, pull matter together to form the first galaxies, stars, and ultimately, us. The most detailed map of this cosmic blueprint came from the European Space Agency's Planck satellite, which spent years measuring these temperature variations with unprecedented sensitivity. The resulting image is often called the universe's first birthday photo, and it is stunningly complex. It looks less like a smooth canvas and more like a pointillist painting or a highly detailed fingerprint. Each speck of color represents a region of slightly higher or lower density in the early universe, but within this beautiful chaos, there is also a surprising degree of order. The patterns exhibit specific statistical properties and symmetries that cosmologists are still working to fully explain. The universe, it seems, came out of the box with a specific set of instructions encoded into its very fabric. Perhaps the most puzzling feature found in this data is what researchers have informally and quite dramatically dubbed the axis of evil. This is not some cosmic supervillain scheme, but a mysterious large-scale alignment in the temperature fluctuations that seems to suggest a preferred direction in space. According to the standard cosmological principle, the universe should be isotropic, meaning it should look the same in every direction, with no special place or orientation. Yet the patterns in the CMB appear to be aligned along a particular axis in a way that defies this fundamental assumption. It's as if the universe has a subtle north and south pole written into its oldest light. While some scientists argue this could be a statistical fluke or an artifact of how we measure the data, its persistence across different satellite missions makes it a genuine anomaly that challenges our core understanding of the cosmos's symmetry. This raises a profound question. Could these patterns be more than just random quantum fluctuations amplified by inflation? What if they represent a form of cosmic information, a code imprinted onto the universe at the moment of its creation? The precise nature of these fluctuations, their specific statistical properties, and even strange alignments like the axis of evil, all hint that the initial conditions of the universe were set with incredible specificity. This doesn't necessarily mean a literal message was written in the microwaves, but it does suggest that the laws of physics might include a set of initial parameters or constraints that guided the evolution of the cosmos in a very particular direction. It's like finding a computer that not only turned on but booted up with a complex operating system already installed and running. This idea of the CMB as a cosmic fingerprint points toward a universe that is not random but intelligently arranged from its very inception. The patterns we see are the direct result of the initial conditions and the physical laws that have operated since then. Their exquisite detail and unexpected features suggest that those initial conditions were finely tuned to produce the rich, complex, and structured universe we observe today. As we move from this universal blueprint to its finished product, we see how these tiny ripples grew into the vast cosmic web of galaxies, the next great anomaly in our journey. If the cosmic microwave background gave us the universe's blueprint, then the large-scale structure we see today is the finished cathedral. For a long time, astronomers assumed that galaxies were scattered more or less randomly throughout the cosmos, like isolated islands in a vast, dark ocean. But as our technology improved and we began to map the heavens in 3 dimensions, a far more astonishing truth emerged. The universe on its grandest scale is not a random splatter of stars and galaxies. It is a magnificent, intricate web, a cosmic architecture of breathtaking complexity and order. This is the Great Cosmic Web, and its discovery fundamentally reshaped our understanding of the universe's structure. Projects like the Sloan Digital Sky Survey have spent decades meticulously charting the positions of millions of galaxies. The resulting 3-dimensional maps are nothing short of awe-inspiring. They reveal a vast network of dense galaxy clusters connected by long, thin filaments of matter, all surrounding enormous, empty regions known as cosmic voids. These voids can be hundreds of millions of light-years across, unimaginably vast bubbles of near-nothingness. The galaxies themselves are not scattered randomly, but are strung along the filaments like pearls on a necklace, congregating at the intersections where multiple filaments meet. This structure isn't just a two-dimensional pattern, it's a three-dimensional lattice that permeates the entire observable universe. It looks less like a random explosion and more like the growth pattern of a crystal, or perhaps even more strikingly, like the neural network of a giant brain. This incredible organization presents a profound puzzle for cosmologists. We understand the primary force at work, gravity. The tiny fluctuations in density we saw in the CMB provided the seeds. Over billions of years, gravity amplified these slight over-densities, pulling matter together to form the galaxies and the vast structures we see. But gravity alone seems insufficient to explain the specific, web-like pattern that has emerged. The process is too efficient, too organized. This is where the mysterious component of dark matter enters the story. Cosmologists believe that this invisible, non-luminous matter forms an unseen scaffolding. Its gravitational pull guides the ordinary, visible matter, the stuff that makes up stars, planets, and us, into the intricate filaments and nodes of the cosmic web. Dark matter acts as the hidden framework upon which the visible universe is built. Yet, even with dark matter in our equations, the sheer scale and precision of this structure remain deeply mysterious. The cosmic web isn't just a physical arrangement of matter. It bears an uncanny resemblance to other complex information processing systems. The network of galaxies mirrors the structure of the Internet, the neural connections in a human brain, and even mycelial networks of fungi that communicate underground. This visual similarity has led mathematicians and theoretical physicists like Gregory Chaitin to propose a radical idea. What if the universe is fundamentally computational? In this view, the cosmic web isn't just a structure, it's a circuit. The galaxies and filaments could be seen as nodes and connections in a vast universe-scale computer, processing information according to some deep, underlying code. The laws of physics themselves might be the algorithms this cosmic computer is running. This perspective transforms our understanding of space from a passive container into an active, dynamic processor. The cosmos isn't simply containing structures. It might be a structure of intelligence where complexity and organization emerge from encoded rules written into the fabric of reality itself. The large-scale structure of the universe, therefore, stands as a powerful third anomaly. It moves beyond the fine-tuning of constants and the patterns of the CMB to show us the tangible, visible outcome of those initial conditions. A universe that has organized itself into a complex, interconnected network that hints at a deeper, more intelligent foundation. And if the universe is connected on this grand, cosmic scale, our next anomaly reveals a connection so intimate and instantaneous that it defies our very understanding of space and time. If the cosmic web shows us a universe connected by gravity on the grandest scales, then our next anomaly reveals a connection so intimate and instantaneous it seems to defy the very fabric of space and time. This is the bizarre world of quantum entanglement, a phenomenon so strange that even Albert Einstein, whose own work helped lay its foundation, found it deeply unsettling. He famously dismissed it as spooky action at a distance because it appeared to violate a core principle of his theory of relativity, that nothing, not even information, can travel faster than the speed of light. Yet, this spooky action is not only real, it's one of the most well-tested and confirmed phenomena in all of physics, forcing us to reconsider the very nature of reality itself. So, what exactly is quantum entanglement? Imagine you have a pair of particles, perhaps 2 electrons or 2 photons, that are created together or interact in a specific way. According to the rules of quantum mechanics, their properties like their spin, polarization, or momentum become linked or entangled. From that moment on, these particles are no longer separate individuals. They form a single, unified quantum system, no matter how far apart they travel. You could separate them by the width of a lab bench or by billions of light years, and this profound connection remains. The truly mind-bending part is that if you measure the property of one particle, the other particle's corresponding property instantly snaps into a correlated state. It's as if the second particle knows the result of the measurement on its partner and adjusts itself accordingly, all without any signal passing between them. For decades, this was a philosophical debate, a troubling paradox at the heart of quantum theory. But in the 1980s, a brilliant French physicist named Alain Aspect designed a series of groundbreaking experiments to put entanglement to the ultimate test. His setup was designed to close potential loopholes that could offer a classical explanation. He ensured that the measurements on each particle were performed so quickly that not even a light-speed signal could communicate between them. The results were unequivocal. The particles were correlated in a way that defied any explanation based on local, hidden information. They were truly connected in a way that transcended space. Aspect's work, which later earned him a Nobel Prize, provided stunning confirmation that Einstein's spooky action was in fact a real feature of our universe. This immediate correlation across any distance challenges our most fundamental concepts of locality and causality, the ideas that objects are only influenced by their immediate surroundings and that cause must precede effect. Entanglement suggests that at a deep, fundamental level, the universe is non-local. Space, the vast emptiness we perceive between stars and galaxies, is not the ultimate separator we thought it was. It may be more like a surface phenomenon, a veil hiding a deeper, interconnected reality where distance is meaningless. This has led some of the most profound thinkers in physics to propose radical new ways of seeing the cosmos. The theoretical physicist David Bohm, for instance, suggested that our everyday reality of separate objects and clear boundaries is an explicate order, a kind of unfolded projection from a deeper, hidden, implicate order. In this underlying reality, everything is enfolded into a unified whole, and entanglement is simply a glimpse of that deeper connectivity poking through into our world. What does this mean for the idea of an encoded cosmos? Entanglement hints at a universe where information is primary and fundamental. The entangled particles behave as if they are part of a single system because, in a very real sense, they are. Their states are not independent, they are written into the same line of cosmic code. This suggests that the universe might operate not as a collection of separate things, but as a unified network where every part is in instantaneous communication with every other part. It's a concept that resonates powerfully with the ancient philosophical idea of the universe as a single, living organism. The intelligence we're searching for may not be an external programmer, but an inherent property of this deeply interconnected whole. A cosmic system where the very act of observation seems to play a mysterious and active role. If the strange connection of quantum entanglement suggests a universe that is fundamentally unified, then our next anomaly asks a question that is perhaps the most personal and profound of all. What is the role of the observer in all of this? What is the place of our own consciousness in a quantum universe? This brings us to one of the most famous and baffling experiments in all of science, the double-slit experiment. At its heart, this experiment reveals a truth so startling that it seems to blur the line between the physical world and the world of the mind, suggesting that the act of observation itself might be a creative force in the cosmos. The classic double-slit experiment is deceptively simple. You have a source that fires particles, say electrons, one at a time toward a barrier with two thin slits in it. Behind the barrier is a screen that detects where each electron lands. If electrons behaved like tiny bullets, you would expect to see two distinct clusters on the screen, directly behind the two slits. But that's not what happens. Instead, as the electrons arrive one by one, they begin to build up a pattern of alternating light and dark bands, known as an interference pattern. This is the unmistakable signature of a wave, like ripples of water passing through two openings and interfering with each other, amplifying in some places and cancelling out in others. The bizarre conclusion is that each individual electron is not going through one slit or the other. It is behaving as if it passes through both slits simultaneously as a wave of possibilities, interfering with itself. Now, here is where the experiment takes a truly weird turn. Scientists decided to place a measuring device by the slits to determine, once and for all, which slit each electron actually goes through. The moment they do this, the magic vanishes. The beautiful interference pattern disappears. In its place, the screen shows just two simple bands. The mere act of observing, of measuring the electron's path, forces it to collapse from a spread-out wave of potential into a single, definite particle with a specific location. It's as if the electron knows it is being watched and changes its behavior accordingly. This isn't just true for electrons. It has been demonstrated with photons, atoms, and even large molecules. The universe at its most fundamental level appears to be responsive to observation. This startling result led some of the 20th century's greatest scientific minds to a radical hypothesis. Brilliant mathematicians and physicists like John von Neumann and Eugene Wigner argued that the measurement device itself couldn't be the cause of the collapse, as it is also made of particles governed by quantum rules. They followed the chain logically. The device interacts with the electron. A scientist reads the device. The scientist's brain processes the information. They proposed that it is ultimately the consciousness of the observer, the awareness that registers the result, that causes the wave function to collapse. In this view, consciousness is not a passive byproduct of the brain, but an active participant in shaping reality. The cosmos is not just something we observe from the outside. It is a participatory universe that requires a mind to bring its possibilities into concrete existence. This idea, often called the Copenhagen interpretation, is of course deeply controversial. Many physicists offer other explanations, like the many worlds interpretation, where every possibility happens in a branching multiverse, or decoherence, where interaction with the environment causes the collapse. Yet the core mystery remains. The undeniable fact is that in the laboratory, the act of observation has a tangible, measurable effect on the outcome of quantum events. This has fueled speculation that goes far beyond physics. It aligns with ancient philosophical ideas and modern notions that the universe might be a kind of mental construction, a vast simulation or a dream where the rules are encoded to respond to awareness itself. Some modern researchers, like those in the field of panpsychism, go even further, proposing that consciousness is not something that emerged from complex brains, but is a fundamental property of the universe, akin to mass or charge, present in some rudimentary form in every particle. What does this mean for our search for cosmic intelligence? The role of consciousness in quantum mechanics presents a fifth profound anomaly. It suggests that intelligence is not just an accidental product of the cosmos, but may be woven into its very fabric. The universe might be built not just of matter and energy, but of mind and meaning, with the act of observation being the mechanism that translates potential into reality. This transforms the cosmos from a cold, mechanical clockwork into a living, responsive system, one that seems to be waiting for us to engage with it, to ask questions, and in doing so, to help complete its own existence. This intimate connection between the inner world of mind and the outer world of space leads us to look for evidence of large-scale intelligence, starting with mysterious alignments on a truly cosmic scale. Leaving behind the intimate dance of particles and the profound role of the observer, we now cast our gaze across the truly staggering expanses of the cosmos to a scale that defies human comprehension. Here, we encounter a phenomenon so vast and coordinated that it seems to whisper of a universe with a hidden sense of direction, a grand architectural plan written in the alignment of its most brilliant beacons. We are talking about quasars, the most luminous and energetic objects in the entire universe. Each one is a ferociously bright active galactic nucleus, a supermassive black hole at the heart of a distant galaxy, feasting on surrounding matter and blasting out enough radiation to outshine every star in its galaxy combined. These cosmic lighthouses are scattered billions of light-years apart, and according to our fundamental cosmological principles, they should be oriented randomly, pointing in every which direction like a universe-sized game of pick-up sticks. Yet that is not what astronomers are finding. In a series of studies that began over a decade ago and continue to this day, researchers like Damien Hutzemakers of the University of Liege in Belgium have made an astonishing discovery. By carefully measuring the polarization and spin axes of the light from hundreds of these quasars, they have found groups of them separated by billions of light-years, whose rotation axes are not random at all. They are aligned with each other. They are all spinning in the same coordinated way, as if connected by some invisible cosmic framework. Imagine dozens of spinning tops scattered across different continents, all mysteriously tilting and rotating in perfect unison. The scale of this coordination is beyond enormous. It is cosmic. The distances involved are so vast that not even a signal traveling at the speed of light could have communicated between them within the entire age of the universe to orchestrate this alignment. They should be completely independent, and yet they are not. This presents a monumental challenge to one of the bedrocks of modern cosmology, the cosmological principle. This principle states that on a large enough scale, the universe is homogeneous and isotropic. It should look the same in every direction and have no special places or preferred axes. There should be no up or down in the cosmos. The alignment of quasars across such unimaginable distances directly challenges this idea. It suggests that there might, in fact, be a preferred direction or a large-scale structure to the universe that we are only just beginning to detect. Some have tentatively linked this to other large-scale mysteries, like the controversial dark flow, a purported systematic drift of galaxy clusters toward a single point in space, which also hints at a universe that is not as uniform as we thought. What could possibly be causing this? Our current models of physics and cosmology have no ready answer. It is not gravity, as the gravitational influence of even the largest known structures couldn't coordinate objects on such a scale. It points toward something far more fundamental, perhaps a property of space-time itself that was imprinted at the moment of creation, a kind of cosmic grain or spin that was woven into the fabric of the universe during its initial inflation. This idea of a built-in preferred direction is as revolutionary as it is unsettling. It implies that the universe might have an intrinsic architecture, an underlying grid or framework that guides the evolution and orientation of its most massive structures. It moves us from a universe of random chance to a cosmos that may have a built-in bias, a subtle directive encoded into its very laws that favors order and alignment on the grandest possible scale. Could this be evidence of a design, a cosmic blueprint that dictates not just the laws of physics but the very arrangement of matter and energy? The coordinated spin of quasars across billions of light-years stands as a powerful sixth anomaly, a silent testament to a universe that is far more interconnected and intentionally ordered than our standard models allow. It suggests that space is not a passive void but an active medium with properties we are only beginning to fathom, properties that might just point toward an intelligent source of its initial conditions. And if the universe is quietly aligning its most brilliant objects, what other messages might it be sending, not through slow, patient alignment, but in sudden, brilliant, and fleeting bursts of raw energy? Just as the vast, slow-motion alignment of quasars hints at a cosmic architecture, the universe also speaks in sudden, brilliant shouts that last barely the blink of an eye. These are fast radio bursts, or FRB, and they are one of the most electrifying and puzzling discoveries in modern astronomy. Imagine a single, millisecond-long blast of radio waves that unleashes more energy than our sun puts out in 80 years. For that tiny fraction of a second, it outshines entire galaxies in the radio spectrum, and then, just as suddenly as it arrived, it's gone. For years after the first one was discovered in 2007, these events were thought to be singular cataclysms, the final death cries of unknown cosmic objects, exploding once and then vanishing forever into silence. But then, everything changed. The game changer was a burst known as FRB 1211-2, discovered in 2012 and pinpointed to a dwarf galaxy 3 billion light-years away. This wasn't a one-off event. It repeated, and it didn't just repeat randomly. It did so with a strange, almost mechanical regularity. In 2020, astronomers announced that this source follows a cycle. It erupts with a frenzy of bursts over a period of about 90 days, then falls completely silent for 67 days before starting the entire process over again. This 157-day cycle is as precise as clockwork. Other repeating FRBs have since been found with their own distinct periodicities, some as short as 16 days. This isn't the behavior of a simple stellar explosion. It's the behavior of a system, a mechanism with a built-in timer. It behaves less like a bomb and more like a lighthouse, with a rotating beam that periodically sweeps across our line of sight. This stunning regularity immediately pushes the boundaries of known physics. The leading natural explanation points to magnetars, a type of neutron star with an unimaginably powerful magnetic field. Perhaps a magnetar's crust is undergoing starquakes, or its intense magnetic environment is funneling energy in a way that creates these incredibly powerful beams. But even these exotic models struggle to account for the precise, clock-like timing of the repetitions over such long cycles. The sheer energy involved and the mind-boggling brevity of the bursts suggest a natural engine of incredible power and precision, one that we have not yet fully imagined. It's a phenomenon that seems to operate at the very edge of what is physically possible. Yet, the extraordinary nature of these signals has led some serious scientists to cautiously entertain an even more profound possibility. Could at least some of these signals, particularly the ones with complex and repeating patterns, be artificial in origin? The esteemed astronomer Avi Loeb, former chair of Harvard's astronomy department, has famously suggested that we must consider all possibilities, including that FRBs could be evidence of advanced technology. He draws a comparison to our own civilization. If we were to build a powerful interstellar beacon to propel light sails across galaxies, the energy signature of such a device would look an awful lot like a fast radio burst. The idea is not that little green men are trying to phone us, but that we might be inadvertently detecting the leakage from unimaginably powerful technologies operating on a galactic scale. It's a hypothesis born not of fantasy, but of the simple logical step that if humanity might develop such technology in the future, another civilization could have already done so in the distant past. This is where the anomaly truly blurs the line. The repeating patterns, the precise periodicities, the incredible energy focused into a narrow band of radio waves. All of these characteristics are exactly what we would expect to see if we were detecting an encoded data stream. They possess a kind of structure that feels informational. It's the difference between hearing the random crackle of static and hearing the distinct patterned pulses of a Morse code message. We don't know what the message says or even if it is one, but the mere suggestion of a pattern forces us to confront the possibility. The cosmos might not just be filled with the silent, slow architecture of aligned quasars, but also with fleeting, high-energy data packets, a galaxy-wide network of information transfer that we are only just beginning to tune into. This doesn't mean every FRB is a sign of extraterrestrial engineers. The vast majority are almost certainly natural, stemming from the incredible and violent physics of neutron stars and black holes. But the existence of even a few that defy easy explanation opens a door. It invites us to consider that space is not a silent void, but a dynamic medium that could be crackling with all sorts of transmissions, both natural and artificial. We are like early radio operators just discovering the airwaves, listening to the hiss of lightning storms but wondering if, buried within the noise, there might be a signal of a different kind. This search for a meaningful pattern in the cosmic static leads us directly to one of the most famous and enduring mysteries in the history of the search for extraterrestrial intelligence. While the repeating patterns of FRBs offer a modern enigma, one signal from the past still stands as the ultimate ghost in the machine, a singular event that has captivated and confounded scientists for nearly half a century. It was a quiet Sunday evening on August 15, 1977, at Ohio State University's Big Ear radio telescope. This massive instrument, essentially a flat, ground-based antenna the size of 3 tennis courts, was methodically scanning the sky as part of the ongoing search for extraterrestrial intelligence, or SETI. It wasn't manned by a team of researchers. It was chugging along automatically, its data outputting onto long, continuous sheets of perforated computer paper. Days later, a volunteer researcher named Jerry Amon was going through that week's readout, a tedious process of looking for any unusual spikes amid the constant background hiss of the cosmos. And then he saw it. On the printout, the signal's intensity was represented by a string of alphanumeric characters. The noise of space typically registers as a 0 or a 1. What Amon saw was a sequence that read 6 equage 5. This wasn't just a blip, it was a massive, powerful surge. So stunned was he by the data that he circled the sequence in red pen and in the margin simply wrote, "Wow." That exclamation of pure, unvarnished astonishment gave the signal its immortal name. The event itself was as clean and perfect as a signal could be. It lasted for exactly 72 seconds, which is precisely how long the Big Ear telescope would fixate on any single point in the sky as the Earth rotated. It rose in intensity and then fell away in a perfect curve, a textbook signature of a celestial source passing through the telescope's field of view. But it was the signal's frequency that was the real kicker. It was a narrowband signal concentrated at exactly 1,420 MHz. That frequency is no random number. It is the emission frequency of neutral hydrogen, the most abundant element in the universe. Decades earlier, physicists Philip Morrison and Giuseppe Cocconi had published a landmark paper suggesting that 1,420 MHz would be the most logical and natural watering hole for interstellar communication. Any technologically advanced civilization, they reasoned, would know this is a universal constant, a quiet channel in the radio spectrum that could be used to shout, "We are here." Across the mind-boggling distances between the stars, the WOW signal wasn't just loud, it was perfectly crafted. It fit the profile of an interstellar beacon exactly. The immediate and obvious question was, what was it? The hunt for a conventional explanation began instantly. Could it have been a secret military transmission? An undiscovered satellite, a reflection of an earthly signal off a piece of space debris, a passing airplane or a ground-based source? For over 4 decades, astronomers have chased down every conceivable lead. They have scrutinized the location in the constellation Sagittarius where it originated. They have looked for comets or asteroids that might have been in the area. They have listened for a repeat transmission with far more powerful modern telescopes, like the Very Large Array. The result has been a resounding and deeply puzzling silence. The signal has never been heard again, not once. Every proposed natural or human-caused explanation has fallen short, unable to account for the signal's unique combination of intensity, frequency, and its one-and-done nature. It remains in a category of its own, the signal that was perfect in every way and utterly alone. This enduring mystery is what makes the WOW signal so powerful. It isn't just data, it's a symbol. It represents the tantalizing possibility that the cosmos might be dotted with brief, brilliant flashes of intelligence, not constant beacons, but perhaps greetings, warnings, or simply the leakage from technologies so vast we can scarcely imagine them, flickering on and off across the galaxy. It's the ultimate cosmic what-if. Jerry Amon himself, though always cautious, never ruled out the possibility of an extraterrestrial origin. He often said that because we didn't have enough data, we must leave it as an unanswered question. But he also admitted that he'd never found a suitable explanation that didn't involve intelligence. The profound lesson of the WOW signal isn't that we found proof of aliens. It's that we found a perfect candidate, a single data point that refuses to be explained away. It challenges the very methodology of science, which relies on repeatability and verification. How do you study a phenomenon that happens only once? It forces us to confront the idea that the universe might not be broadcasting on a schedule we can easily understand. Its messages might be rare, fleeting, and incredibly easy to miss if you're not looking at exactly the right place at exactly the right time. This single event, a few characters on a dot matrix printout, underscores the critical importance of continuing to listen, to question, and to remain open to the astonishing. It suggests that each unexplained blip on our instruments could be a piece of a puzzle so large we can't yet see its shape. And this very idea that the cosmos might be filled with information waiting to be read leads us directly to a revolutionary way of thinking about reality itself. But if these fleeting signals are like mysterious messages flickering in the dark, what if the very medium they travel through, space itself, is the message? This brings us to a revolutionary idea that is perhaps the most profound shift in our understanding of reality since quantum mechanics. It's the concept that information is not just something we send through the cosmos, but the very substance from which the cosmos is made. This is cosmic information theory, and it proposes that the universe might not be fundamentally built of matter and energy, but of bits, not physical atoms, but abstract units of information. The journey to this astonishing idea began not in a physics lab, but at Bell Telephone Laboratories in the 1940s. A brilliant mathematician named Claude Shannon was trying to solve a very practical problem: how to send a clear, unambiguous message over a noisy telephone line. In the process, he founded the field of information theory. Shannon's genius was to separate the meaning of a message from its pure information content. He defined information mathematically as a series of binary choices, ones and zeros, yeses and nos, that could be used to encode anything from a sonnet to a symphony. His work gave us the bit, the fundamental unit of information, and laid the groundwork for the entire digital revolution. but the implications would eventually reach far beyond our computers, stretching out to the very edges of the cosmos. In the decades that followed, visionary physicists began to ask a breathtaking question. If information is what allows us to describe and understand the universe, could it be that information is what the universe actually is? The legendary physicist John Archibald Wheeler, who helped shape much of 20th century physics, became a passionate advocate for this idea. He coined a famous and enigmatic phrase, "it from bit." Wheeler proposed that every particle, every force field, and even the very fabric of space-time itself ultimately derives its existence from immaterial bits of information. In this view, the physical world, the it is not primary. It emerges from the answers to a vast number of yes or no questions, the bits. The universe is not just described by mathematics, it is, at its heart, a gigantic, ongoing computation. This line of thinking leads to some truly mind-bending theories. Digital physics is one such idea, suggesting that the universe is literally a computational system, akin to an unimaginably vast and powerful computer. In this model, the laws of physics are not just equations in a textbook, they are the operating system's algorithms. The unfolding of time is the processing of these algorithms. What we perceive as the smooth, continuous flow of reality might actually be the result of discrete, tiny computational steps happening at the smallest possible scale, the Planck scale. It's a vision of the cosmos as a cosmic CPU, calculating its own evolution moment by moment. Then there is the holographic principle, an idea born from the study of black holes. Physicists discovered that all the information describing everything that ever fell into a black hole is not lost inside its mysterious interior. Instead, it is somehow encoded on its two-dimensional surface, the event horizon. It's as if the black hole's entire three-dimensional contents are projected from a flat, two-dimensional screen like a hologram. This led to the radical proposal that our entire universe might work the same way. The three-dimensional reality we experience, with its galaxies, chairs, and people, might be a projection from a two-dimensional surface at the boundary of the universe. In this view, we are all living inside a cosmic hologram, and the apparent depth and solidity of the world around us is an incredibly convincing illusion generated from information encoded on a distant, flat surface. This perspective completely transforms our understanding of space. It is no longer a passive, empty stage. It is an active processor, a dynamic medium buzzing with information transfer and computation. The vacuum of space is not truly empty. It is saturated with potential information, a seething foam of quantum possibilities where bits are constantly flipping. The intelligence we've been searching for in the anomalies might not be an external programmer, but the inherent nature of reality itself, a universe that is, in its essence, cognitive. It thinks, it computes, and it manifests. This doesn't make it any less real, it makes it far more astonishing. We are not just living in the universe, we are processes within a cosmic mind, patterns in the great computation. And if the universe is indeed built on a foundation of information, it would make perfect sense for that information to be expressed in patterns of breathtaking beauty and mathematical harmony. If the universe is fundamentally built of information, we might expect to see its signature not just in the abstract, but etched into the very shape and structure of everything we observe. And indeed, we find a mathematical pattern so pervasive and so beautiful that it seems to whisper of a deep, underlying harmony in the cosmos. It appears in the curve of a nautilus shell, the arrangement of seeds in a sunflower, and the spiral arms of a distant galaxy. This is the golden ratio, often denoted by the Greek letter phi, approximately equal to 1.618. It is an irrational number, a constant that emerges from a simple property. If you divide a line into two parts so that the ratio of the whole to the larger part is the same as the ratio of the larger part to the smaller part, you have just divided it by the golden ratio. This proportion has fascinated mathematicians, artists, and architects for millennia because of its unique aesthetic appeal. But its appearance throughout the natural world, and even in the cosmos, suggests it might be more than just a human preference for a certain shape. It might be a fundamental principle of efficient growth and structure. Closely tied to the golden ratio is the Fibonacci sequence, a series of numbers where each number is the sum of the two preceding ones, 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on, stretching into infinity. As the sequence progresses, the ratio between successive Fibonacci numbers gets closer and closer to the golden ratio. This mathematical relationship manifests in stunning ways. Look at a pine cone or a pineapple, and you'll see its scales or segments arranged in intersecting spirals. Count these spirals, and you will almost always find a pair of adjacent Fibonacci numbers, like 5 and 8 or 8 and 13. This isn't a random accident of botany. It is the most efficient way to pack the most seeds or leaves into a given space, ensuring each one has access to sunlight and nutrients without being crowded out by its neighbors. It is a pattern of optimal packing that evolution has discovered again and again. But this is not a pattern confined to our planet. We see this same mathematical signature written across the night sky in the most majestic of forms, spiral galaxies. Our own Milky Way, along with iconic galaxies like Messier 74 and the Pinwheel Galaxy, displays arms that unwind in a graceful logarithmic spiral, a shape whose growth factor is defined by the golden ratio. The arms don't spiral at a constant rate. They tighten in a way that can be described by phi. Why would vast collections of billions of stars, governed by the simple force of gravity, arrange themselves according to this specific mathematical principle? One compelling explanation lies in the physics of density waves, where stars and gas travel through regions of higher density, creating the appearance of bright arms. But the fact that this process so often results in a golden spiral suggests an underlying efficiency or stability to this form, as if the universe has a preferred blueprint for creating order on a grand scale. The influence of this cosmic mathematics doesn't stop at galactic shapes. There is fascinating, though more speculative, evidence that the golden ratio might even govern the rhythms of our solar system. When you look at the average distances of the planets from the Sun, expressed in astronomical units, a curious pattern emerges. The ratios of the orbits of successive planets sometimes come remarkably close to phi or its square. For instance, the ratio of Jupiter's orbit to Mars's orbit is about 1.63, very near the golden ratio. While these ratios are not perfect and the field of celestial harmony is fraught with cherry-picked data, the persistent appearance of these numbers is intriguing. It hints that the same principles of resonance and harmonious proportion that work on a small scale might also be operating on a scale of millions of miles, governing the architecture of planetary systems. This pervasive presence of phi and Fibonacci sequences points toward a universe that is not just built with mathematics, but with a specific kind of mathematics, one that favors efficiency, beauty, and growth. It implies that the cosmos has an inherent aesthetic, a tendency toward forms that are both functionally optimal and visually pleasing. This is a powerful argument against a universe of pure random chance. Chaos does not consistently produce elegant spirals and efficient packings. Intelligence often does. It suggests that the laws of physics may be tuned not only for the existence of life, but for the emergence of a certain kind of order and beauty. The universe appears to be following a recipe, a set of instructions for building complexity that is written in the language of mathematics. And if this mathematical code is so universal, we might expect to find other numerical signatures hidden within the fabric of reality, patterns that are not about beauty and growth, but about uniqueness and security. If the elegant spirals of the golden ratio suggest a universe with an inherent sense of beauty, then the next anomaly points toward a cosmos that values something else entirely: security and uniqueness. This brings us to the strange and stubborn prevalence of prime numbers. These are the mathematical atoms, the fundamental building blocks of all other numbers. A prime number is any whole number greater than 1 that cannot be formed by multiplying two smaller whole numbers. They are the loners of the numerical world, divisible only by themselves and 1. Numbers like 2, 3, 5, 7, and 11 are primes, standing defiant against being broken down. For centuries, mathematicians have been fascinated by their apparent randomness. They seem to pop up without a predictable pattern, yet they are infinite in number, becoming less frequent but never-ending as we count higher into the number line. This combination of fundamental importance and erratic behavior is what makes their appearance in the natural world so deeply puzzling and suggestive. One of the most famous and clear-cut examples of this is the life cycle of the North American periodical cicada. There are several species of these insects, and some of them, known as Magicicada, emerge from the ground in massive, synchronized broods only once every 13 or 17 years. They spend over a decade and a half developing underground as nymphs, then all surface within a few weeks to mate, lay eggs, and die, creating a deafening natural spectacle. The crucial detail here is that both 13 and 17 are prime numbers. Evolutionary biologists have a compelling theory for why this would be an advantage. The cicada's goal is to avoid syncing up with the life cycles of their predators. If a predator has a population boom every 2 years, or every 4 years, or every 6 years, it will rarely, if ever, coincide with a cicada emergence that only happens on a prime-numbered schedule. A prime-numbered cycle makes it incredibly difficult for any other organism with a periodic life cycle to reliably predict and exploit them. It is a brilliant, naturally evolved strategy that uses the mathematical property of primes to ensure survival. But we see this mathematical signature in quieter forms as well. In the world of botany, the arrangement of leaves around a stem, known as phyllotaxis, often follows patterns that involve Fibonacci numbers, which, as we've seen, are closely related to the golden ratio. However, the underlying efficiency of this arrangement can also be understood through the lens of primes. It minimizes overlap between leaves, giving each one the best possible access to sunlight and rain. This efficient packing, avoiding common divisors, is a spatial analog to the cicada's temporal strategy. Even the seemingly random darting of an animal evading a predator has been analyzed and shown to follow a pattern that is mathematically ergodic, a complex concept that, at its heart, relies on avoiding predictable periodic cycles, much like the unpredictable distribution of prime numbers themselves. This practical use of primes in nature for evasion and efficiency finds a direct parallel in our most advanced human technology, cryptography. The entire foundation of modern digital security, from your online banking to private messages, rests on the mathematical properties of prime numbers. Encryption systems like RSA use the fact that while it is easy to multiply two large prime numbers together, it is astronomically difficult and time-consuming to take the resulting huge number and factor it back into the two original primes. This one-way function is what keeps digital information secure. The universe, it seems, has been using this same principle for millions of years. The cicada's prime numbered life cycle is a form of biological encryption, making their emergence a secret that is computationally infeasible for their predators to crack. This connection is what lifts the phenomenon from a curious oddity of biology to a profound cosmic anomaly. It suggests that prime numbers are not just human intellectual abstractions. They may represent a fundamental principle of stability and information security woven into the fabric of reality. If evolution can stumble upon this principle to ensure the survival of an insect, could the cosmos itself use similar rules on a grander scale? Some scientists have speculated that the timing of pulsars, incredibly dense, spinning neutron stars that emit beams of radiation with the regularity of a cosmic lighthouse, might contain patterns or intervals that relate to prime numbers. The idea is that an intelligent civilization might use such a fundamental, mathematical pattern as a basis for a beacon, a universal calling card. While no such pattern has been conclusively found, the very fact that we are looking for it demonstrates how compelling the idea is. The prevalence of primes hints that the universe might have a built-in bias toward systems that are robust, difficult to predict, and inherently secure, a signature of a very sophisticated kind of underlying logic. It is as if nature has a favorite, unbreakable code, and it is written in the language of mathematics. This drive toward creating secure and complex systems stands in stark contrast to one of the most fundamental laws of physics, which states that everything should be moving toward disorder. If the prevalence of prime numbers suggests a universe that values security and uniqueness, our next anomaly presents what seems like a direct contradiction to the most fundamental rule of reality, a rule that says everything must eventually fall apart. This is the second law of thermodynamics, a principle as grim as it is absolute. It states that in any closed system, disorder, what physicists call entropy, always increases. The universe, in its totality, is the ultimate closed system, and according to this law, it should be on a one-way trip to a featureless, lukewarm soup of particles, a state of maximum disorder known as heat death. Everything should be winding down, decaying, and dissolving into chaos. Yet, when we look around, we see the exact opposite happening. We see stars igniting, planets forming, hurricanes organizing themselves, and life blossoming into breathtakingly complex and intricate forms. This is the entropy paradox, and it is one of the most profound mysteries in all of science. How does complexity emerge in a universe that is supposedly doomed to disorder? To understand this paradox, we need to reframe what the second law actually says. It doesn't forbid local decreases in entropy. It just insists that any local increase in order must be paid for with a greater increase in disorder somewhere else. A classic example is your home refrigerator. Inside the fridge, it gets colder and more ordered as heat is removed. But this only happens because the motor in the back is working hard, expelling even more heat and disorder into your kitchen. The system of fridge plus kitchen sees a net increase in entropy. The universe operates on the same principle, but on a cosmic scale. The immense gravitational collapse that forms a star is a massive increase in local order, creating an incredibly hot, dense, and structured object. But this process releases a staggering amount of energy and radiation out into space, increasing the overall entropy of the universe far more than the order gained within the star itself. Gravity is a master at this. It can pull matter together into beautiful, complex structures like galaxies and solar systems, but it does so by serving as the universe's ultimate entropy engine, driving the overall trend toward disorder even faster. This is where the work of visionary scientists like Ilya Prigogine becomes essential. Prigogine, who won a Nobel Prize for his contributions, studied what are called dissipative structures. These are systems that are far from thermodynamic equilibrium. They are open, constantly exchanging energy and matter with their environment. Think of a whirlpool in a river. The whirlpool is a stable, organized structure, but it can only maintain that beautiful spiral by constantly dissipating the energy of the flowing water around it. It exists at the sweet spot between order and chaos. Prigogine showed that under the right conditions, these systems don't just resist decay, they spontaneously self-organize. They leap into greater complexity. A hurricane is a dissipative structure feeding on the warm ocean to maintain its terrifying organization. Every living thing on Earth, from a single cell to a human being, is a dissipative structure. We maintain our intricate order by taking in energy from the sun, through food, and expelling waste heat and molecules back into our environment, thereby increasing the universe's total entropy to sustain our local pocket of complexity. This changes the entire narrative of the cosmos. The universe isn't just mindlessly sliding toward disorder. It has innate, natural tendencies to spawn complex, self-organizing systems wherever there is a flow of energy to sustain them. The laws of physics and chemistry contain within them a built-in bias for creating order out of chaos under the right conditions. It's not a violation of the second law. It's a glorious and sophisticated consequence of it. The universe doesn't just evolve, it innovates, it experiments, it finds new and more intricate ways to dissipate energy, and in the process it creates galaxies, stars, planets, life, and consciousness. This isn't a random accident, it appears to be a fundamental feature of the cosmic machinery. This drives us to a breathtaking question. Could this tendency toward self-organization and complexity be a form of nascent intelligence woven into the fabric of physical law? Is the universe, in its relentless drive to create structure, actually following a kind of recipe, a set of encoded principles that favor the emergence of mind? The emergence of complexity against the tide of entropy is a powerful 12th anomaly. It suggests that the cosmos is not a sterile void gradually running down but a fertile ground, primed for the spontaneous arising of order, life, and perhaps even meaning. This inherent drive for creation points toward a universe that is fundamentally creative and fecund, setting the stage for the most complex structures of all. But to understand how these structures, galaxies, and vast cosmic webs could even form, we must now turn to the hidden forces that shape them, the mysterious and unseen architects of the cosmos, dark matter and dark energy. But if the emergence of complexity shows us a universe that can spontaneously create order, the next anomaly reveals the mysterious, invisible forces that make this entire cosmic project possible in the first place. We now arrive at perhaps the most humbling discovery in all of modern cosmology, the fact that everything we have ever seen, touched, or studied, every star, every planet, every human being, constitutes a mere 5% of the universe. The remaining 95% is made of stuff we cannot see, cannot touch, and do not understand. This is the dark universe, dominated by two enigmatic components, dark matter and dark energy. They are the unseen architects, the hidden directors of the cosmic play, and their precise, fine-tuned effects suggest they may be the most profound evidence yet for an intelligently structured reality. Let's start with dark matter. The story of its discovery begins with a woman named Vera Rubin, an astronomer who in the 1960s and 70s was meticulously measuring the rotation speeds of stars within spiral galaxies. According to Newton's laws of gravity, stars on the outer edges of a galaxy, far from the central mass, should orbit much more slowly than those near the center. Think of our solar system. Pluto, way out on the edge, crawls along in its orbit compared to Mercury, which zips around the sun at a blistering pace. But what Vera Rubin found was astonishing. The stars at the outskirts of galaxies were moving just as fast as those near the center. The galaxies were rotating so quickly that, based on the amount of visible matter they contained, they should have flown apart long ago. The only possible explanation was that there was far more matter in the galaxy than we could see, a huge, massive halo of some invisible substance whose gravity was the only thing holding these spinning galaxies together. This invisible glue is what we now call dark matter. We now know that this dark matter forms an immense, unseen scaffolding throughout the entire cosmos. It is the framework upon which the visible universe is built. In the early universe, after the Big Bang, ordinary matter, the protons, neutrons, and electrons that make up everything we know, was too hot and energetic to clump together effectively. But dark matter, which does not interact with light or other electromagnetic forces, was immune to this pressure. It began to collapse under its own gravity first, forming vast gravitational wells. It was only later that ordinary matter, the stuff we are made of, was drawn into these pre-existing dark matter wells, cooling and condensing to form the very first galaxies and stars. Without this dark matter scaffolding, the universe would be a formless, featureless sea of gas. There would be no galaxies, no stars, no planets, and certainly no us. It is the silent, invisible architect of cosmic structure. Then there is dark energy, an even more mysterious and counterintuitive force. For much of the 20th century, scientists debated whether the expansion of the universe, set in motion by the Big Bang, would eventually slow down, reverse into a big crunch, or continue forever at a gradually decreasing rate. In the late 1990s, two independent teams of astronomers were observing distant supernova to measure this deceleration. To their absolute shock, they discovered the opposite. The expansion of the universe is not slowing down at all. It is speeding up. Something is acting against the powerful pull of gravity on a cosmic scale, pushing galaxies apart from one another at an ever-increasing rate. This mysterious something was dubbed dark energy. It behaves like a kind of anti-gravity, an inherent property of empty space itself that causes it to expand. The existence of dark energy points to a universe with an incredibly precise and delicate balance. The amount of dark energy, often referred to as the cosmological constant, is fine-tuned to an almost absurd degree. If it were even slightly stronger, the universe would have expanded so rapidly that no galaxies or stars could ever have formed. If it were slightly weaker, gravity would have caused the entire cosmos to collapse back in on itself billions of years ago. The value is perfect for allowing just enough time for structures to form and life to emerge. This precise calibration is one of the greatest unsolved problems in physics. Why does empty space have this specific energy density? It seems as if the vacuum itself has been programmed with a very particular value to enable a complex and long-lived universe. This leads to some extraordinary speculation. Could dark matter and dark energy be more than just unknown particles or fields? Could they be manifestations of a deeper level of reality, perhaps even a form of cosmic information processing? Theoretical physicist Lisa Randall, among others, explores the idea that our visible universe might be a three-dimensional brain existing within a higher dimensional space, and that dark matter could be matter from another dimension whose gravity leaks into ours. Others suggest that the dark sectors could contain their own rich physics, potentially even complex interactions that resemble computation. If the universe is indeed a kind of quantum computer, as some theories propose, then dark matter and energy could be part of its underlying hardware, the unseen processors and memory that govern the visible output we experience. This anomaly forces a profound shift in perspective. we must accept that the reality we perceive with our eyes and instruments is just the tip of the cosmic iceberg. The vast majority of the universe is hidden from us, operating by rules we have not yet deciphered. What we call empty space is not empty at all. It is saturated with dark energy. The gaps between stars are not void. They are filled with the invisible scaffolding of dark matter. This hidden architecture, with its perfect fine-tuning, suggests that the cosmos is built on a foundation of deep, sophisticated principles. It hints that what we see is just the surface level of a far more complex and possibly intelligently coded reality. And if the very structure of space is governed by these hidden forces, it makes us wonder about the nature of the dimension in which all this architecture unfolds, the mysterious and relentless flow of time itself. We've seen how dark matter and dark energy act as the invisible architects of cosmic structure, shaping the universe from behind the scenes. But this grand architectural project doesn't unfold in a static realm. It happens within the relentless, one-way flow of time itself. This brings us to one of the most fundamental and personal mysteries of all, the arrow of time. We all experience time as moving in one direction. Eggs scramble but never unscramble. Memories are made but never unmade. We grow older, never younger. This inexorable forward march from past to future feels so intuitive that we rarely stop to ask, why is there a direction to time at all? The shocking answer from physics is that at the most fundamental level, the laws of physics don't actually care about time's direction. The equations that govern particles work perfectly well whether time is running forward or backward. This profound disconnect between our experience and the underlying laws of reality is the heart of the mystery, and it points directly back to the very beginning of everything. The key to unraveling this puzzle lies in a concept we touched on earlier, entropy, which is the measure of disorder in a system. The second law of thermodynamics gives us the only physical law that has a built-in arrow of time. It states that the total entropy of a closed system always increases. The universe, as the ultimate closed system, is on a one-way journey from a state of low entropy in the past to a state of maximum entropy, or heat death, in the future. So our experience of time's flow is essentially our experience of the universe becoming more disordered. But this just pushes the question back a step. Why was the entropy of the universe so incredibly low in the first place? The early universe, just moments after the Big Bang, was in a state of exquisitely fine-tuned order. The matter and energy were distributed with a smoothness and uniformity that is almost impossible to comprehend. This was the cosmic equivalent of a perfectly pristine, clean room, a state of incredibly low entropy. It is this initial condition that wound up the cosmic clock, giving it a direction to run. This presents us with a monumental why question. Why did the universe start in such a special, ordered state? As the physicist Sir Arthur Eddington, who coined the term arrow of time, pointed out, the entire narrative of cosmic history, the formation of galaxies, the birth of stars, the rise of life, and the very possibility of consciousness depends entirely on this initial low entropy condition. Without it, the second law wouldn't function, complexity could never emerge, and time would have no discernible direction. It would be a universe of random, fluctuating equilibrium with no story to tell. The fact that it did start this way seems like the ultimate act of cosmic fine-tuning. It's as if the universe was pre-programmed with a narrative arc, a story with a beginning, a middle, and an end. This has led to some of the most profound speculation in all of cosmology. Some physicists, like the Nobel laureate Roger Penrose, propose that this low entropy beginning is so statistically improbable that it cannot be a one-off accident. He suggests a model of a cyclic or conformal cosmology, where the universe goes through an endless series of cycles. In his view, a future state of maximum entropy somehow resets itself back to a new low-entropy Big Bang, though the mechanism for this remains highly theoretical. Others see the initial conditions as evidence of something more intentional. The universe appears to have been set up with a specific goal in mind, the creation of complexity and, ultimately, observers who can witness it. In this view, the arrow of time isn't just a passive byproduct of physics. It is an active driver of cosmic evolution. It is the mechanism that allows for the universe to learn about itself, to process information, and to build upon what came before. Time becomes the canvas on which the universe paints its masterpiece of increasing complexity. This transforms our understanding of reality from a static, frozen block into a dynamic, unfolding process. The universe is not merely a collection of things in space, it is a story happening in time. The arrow of time gives the cosmos a history and a future, a memory and a potential. It allows for causality, for learning, and for growth. This challenges us to see the cosmos not as a cold, mechanical clock, but as a living, evolving narrative. The intelligence we've been searching for in the anomalies may not be found in a static set of laws, but encoded into the very progression of time itself, guiding the plot of the cosmic story toward an unknown destination. This sense of a cosmos moving in a coordinated temporal dance leads us to look for similar coordination in the motion of celestial bodies themselves. The dance of the cosmos is not a chaotic free-for-all. It is a performance of breathtaking precision where partners move in perfect, locked steps across millions of miles. Look no further than our own moon, a constant companion that has watched over Earth for billions of years with a single, unchanging face. This is no accident of placement. We are witnessing a phenomenon called tidal locking, a gravitational embrace so intimate that the moon's rotation on its axis has been perfectly synced to its orbit around our planet. It takes the moon the same amount of time to spin once as it does to complete one full journey around us, a graceful pirouette that forever keeps one side hidden from our view. This synchronization creates a stable, predictable relationship, a celestial partnership that has helped regulate Earth's climate and tides over eons, providing a steady rhythm that may have been crucial for the slow, patient emergence of life. But this is just a simple duet in a universe that composes entire symphonies. Venture out to Jupiter, the solar system's gigantic king, and you will find a miniature solar system of its own, with moons that perform an orbital ballet of stunning complexity. 3 of its largest moons, Io, Europa, and Ganymede, are locked in a gravitational resonance so precise it could be set to a metronome. For every single orbit that Ganymede, the farthest of the 3, completes around Jupiter, Europa completes exactly 2 orbits, and the volcanic moon Io completes exactly 4. This 1:2:4 ratio is maintained with impeccable timing, their gravitational pulls gently tugging on each other in a perpetual, rhythmic dance that keeps their orbits stable and prevents them from careening into chaos or drifting away. It's a self-correcting system, a gravitational feedback loop that has likely persisted for billions of years. These harmonies are not rare cosmic quirks. They are a fundamental feature of how planetary systems evolve and stabilize. We see it in the way Neptune and Pluto, though their paths are vastly different, avoid collision because for every 2 orbits Neptune makes around the Sun, Pluto makes 3. We see it in the gaps within Saturn's glorious rings, where the gravitational influence of its moons clears out particles that would naturally orbit in sync with them, creating dark bands in the icy tapestry. Astrophysicists explain these resonances through the relentless and predictable mathematics of gravity. Over immense stretches of time, the gentle, repetitive tugs between orbiting bodies add up, energy is transferred, and their orbits naturally evolve toward these stable, integer ratios, like pendulums of different lengths eventually falling into sync when placed on the same wall. Yet the sheer elegance and prevalence of these patterns provoke a deeper question. Why does the universe seem to favor such perfect mathematical relationships? The gravitational explanation tells us how it happens, but it doesn't fully address the profound sense of order it reveals. It feels less like a random outcome and more like a preferred state, as if the cosmos has a built-in inclination for rhythm and balance. This recalls the ancient concept of the music of the spheres, the philosophical idea that the movement of celestial bodies creates a kind of inaudible harmony, a hidden music based on mathematical proportions. In a modern context, it begins to sound less like poetry and more like a potential feature of a coded reality. Could these orbital resonances be a physical manifestation of the universe's underlying mathematical nature? They act as stabilizing algorithms in the cosmic software, ensuring that systems don't crash, that orbits remain predictable over astronomical timescales, and that environments can remain stable long enough for the delicate process of life to potentially take root. This cosmic choreography, where moons and planets move as if guided by an unseen conductor, suggests a universe that is not just ordered but intelligently orchestrated. The stability granted by these synchronizations is what allows for the long-term conditions necessary for planets to be habitable, for solar systems to persist, and for astronomers to even exist to observe them. It is a silent, rhythmic testament to a reality that values harmony and persistence, inviting us to consider that the intelligence encoded into the cosmos might not just be in its laws, but in the beautiful, stable patterns those laws produce. This intricate coordination between physical bodies naturally leads us to ponder an even more intimate connection: the possibility that life and consciousness are not mere passengers in this grand scheme, but central to its very purpose and design. But if the precise choreography of the cosmos suggests an underlying order, what if that order isn't just physical but deeply personal? What if the universe doesn't merely permit life and consciousness, but actually requires them to exist at all? This radical idea forms the heart of our next anomaly, a theory that turns the entire traditional scientific narrative on its head. For centuries, science has largely followed a materialist view. The universe is a collection of physical stuff, and consciousness is a late-arriving accident, a fragile flame that flickered to life in the warm corners of a few planets after billions of years of mindless cosmic evolution. But what if we have it completely backwards? This is the provocative proposal of biocentrism, a theory championed by renowned scientist and theoretician Robert Lanza. Biocentrism, at its core, places biology before physics. It argues that life and consciousness are not accidental byproducts of the universe, they are its fundamental, central features. Lanza proposes that what we perceive as the external world, with its vast spaces, flowing time, and solid matter, cannot exist independently of the consciousness that observes it. In this view, space and time are not the absolute, external containers described by Newton or even the flexible fabric of Einstein. Instead, they are tools of the mind, the very framework our consciousness uses to organize and make sense of experience. They are the lenses through which we see, not the reality that is seen. Without a conscious observer to hold them together, the concepts of past, present, future, and distance simply dissolve into a blur of potentiality. This idea finds startling support in the bizarre world of quantum mechanics, which we explored earlier. The double-slit experiment and the observer effect demonstrate that at the subatomic level, that particles exist in a fuzzy state of probability until a measurement is made, collapsing them into a definite reality. Biocentrism takes this a step further, suggesting it is not the measurement device, but the consciousness behind it that is ultimately responsible for this collapse. The universe, in a very real sense, remains in a state of potential until a conscious mind interacts with it, effectively bringing it into being. This would explain why the laws of the universe appear so exquisitely fine-tuned for life. It's not that the universe was designed for us, but that our consciousness is co-creating the universe we perceive, and it naturally creates one compatible with its own existence. This perspective radically reinterprets famous puzzles like the Anthropic principle. Instead of asking, why is the universe so perfectly suited for us? Biocentrism suggests the question is backwards. The universe is suited for us because our consciousness is what gives it form. Death, in this model, becomes a particularly intriguing concept. Lanza, drawing on ideas from quantum physics and the nature of time, suggests that consciousness may not be confined to the brain and may not end with the body's death. If time is a mental construct, then the linear progression from birth to death might be an illusion. Consciousness could be a fundamental property of the universe, like mass or energy, and what we experience as an individual life might be just one point of view of a much larger, eternal consciousness. Of course, biocentrism is highly speculative and lies far outside the mainstream of current scientific thought. Critics argue it is less a testable scientific theory and more a philosophical framework, verging on a form of idealism that has been debated for centuries. It raises difficult questions. If a tree falls in a forest and no one is around to hear it, does it make a sound? Biocentrism would say no, not just in terms of sound waves, but the tree itself might not exist in a definite state without an observer. This seems to contradict our common-sense experience of a persistent, objective world. Yet, its power lies in its ability to elegantly weave together several of our deepest anomalies: quantum indeterminacy, the role of the observer, and cosmic fine-tuning, into a single, coherent, if mind-bending picture. If biocentrism is even partially correct, it represents the ultimate expression of an encoded cosmos. The intelligence we've been searching for is not embedded in the universe. The universe is that intelligence, a conscious entity experiencing itself through an infinite multitude of perspectives. We are not just studying the universe, we are the universe studying itself. This dissolves the separation between observer and observed, between the mind and the cosmos, suggesting a reality that is ultimately mental and participatory. This breathtaking idea naturally leads us to another modern framework that also reimagines the nature of reality, one that replaces a conscious universe with a programmed one. If biocentrism suggests the universe is a conscious mind, then the simulation hypothesis proposes an even more startling alternative, that it might be a sophisticated computer program and we are characters living inside it. This idea, powerfully articulated by the philosopher Nick Bostrom at the University of Oxford, is not science fiction, but a serious argument based on a logical progression of current technological trends. Bostrom's reasoning is as elegant as it is unsettling. He begins with a simple trilemma, a set of three possibilities. He argues that at least one of the following statements must be true. First, that almost all civilizations at our level of technological development go extinct before they become advanced enough to create realistic simulations. Second, that almost all advanced civilizations lose all interest in creating simulations of their ancestors. Or third, that we are almost certainly living inside a computer simulation right now. When you consider the staggering pace of our own progress in computing and virtual reality, the first two options begin to feel like unlikely assumptions, making the third possibility disturbingly plausible. The evidence for this idea is not found in a single smoking gun, but in a convergence of clues hidden in the very fabric of physics. The first and perhaps strongest clue is the deeply mathematical nature of the universe. The laws of physics are not just described by mathematics, they are mathematics. They can be written down as elegant equations that perfectly predict the behavior of reality. This is incredibly odd. Why should the universe be comprehensible to our minds at all? And why should it obey these precise, abstract rules? If the universe were a simulation, this would make perfect sense. The mathematical laws would simply be the code upon which the simulation is running, the algorithms that govern everything from the orbit of planets to the bonding of atoms. The universe behaves like a program because, in this view, it literally is one. Then there is the issue of resolution. In any digital simulation, whether it is a video game or a scientific model, there is a limit to how small you can go. You cannot render an infinitely small detail. There is a fundamental pixel size, a smallest possible unit. Our universe appears to have exactly that. It is called the Planck length, a distance so vanishingly small that it is a millionth of a billionth of a billionth of a billionth of a centimeter. Below this scale, the very concepts of space and time lose all meaning. This is exactly what we would expect to find if our reality was being rendered on a cosmic computer with finite processing power. The universe has a built-in resolution limit, much like the pixels on your screen. Quantum mechanics provides perhaps the most compelling glitches in the matrix. The bizarre behavior of particles, existing in multiple states at once until observed, fits neatly into the framework of a simulation. In a video game, to save on processing power, a program does not render every detail of a faraway mountain until a player looks at it. It only calculates the precise details when observation demands it. This is called a rendering distance. The quantum world acts in a strikingly similar way. Particles exist in a fuzzy, probabilistic state, a state of unrendered potential, until an observation forces the system to commit to a specific outcome, to render a definite reality. This observer effect could be the universe's way of optimizing its computational load, only calculating the precise details of reality when absolutely necessary. This hypothesis has moved from the fringes of philosophy into mainstream conversation, championed by prominent figures like Elon Musk, who has pointed out that given the rapid advancement of our own video games from simple pixels to near photorealism, a future civilization's simulations would be indistinguishable from reality. The logical conclusion is that the odds we are in the base reality are astronomically low. This idea transforms our search for cosmic intelligence. It suggests that the anomalies we have been exploring, the fine-tuning, the quantum oddities, the mathematical patterns, are not evidence of a divine creator, but perhaps of a programmer. The quest becomes not to find God, but to find the user, or perhaps to understand the source code. It reframes every mystery as a potential feature or a bug in the system, inviting us to look for more clues in the numerical constants that form the bedrock of this apparent reality. Stepping away from the grand architecture of simulations and conscious universes, we find ourselves staring at a different kind of evidence, one written not in vast structures but in the quiet, persistent language of numbers themselves. Scattered throughout the laws of physics are certain numerical values that appear with such precise and perfect consistency that they feel less like discovered facts and more like fundamental pieces of a cosmic code. These are the dimensionless constants, and their values are so exquisitely calibrated that even the slightest alteration would unravel the very fabric of reality as we know it. Consider the ratio of the mass of a proton to the mass of an electron. This number is approximately 1,836. Why this specific value? If it were even marginally different, the consequences for chemistry would be catastrophic. A smaller ratio would make hydrogen atoms less stable, potentially preventing them from forming at all. A larger ratio would disrupt the delicate energy levels within atoms, making the complex bonds necessary for molecules like DNA impossible. This number sits in a breathtakingly narrow sweet spot that allows for the existence of all the rich chemistry that underpins life. It is not a number derived from any deeper theory. It is an input, a parameter that seems to have been set with incredible precision. This is not an isolated case. The fine structure constant, represented by the symbol alpha, governs the strength of the electromagnetic force. Its value, approximately 1/137th, is another fundamental puzzle. It dictates how atoms hold together, how light interacts with matter, and why stars shine. Physicist Richard Feynman called it one of the greatest damn mysteries of physics, a magic number that we don't understand at all. Then there are the transcendental numbers that seem to be woven into the very geometry of existence. Pi, the ratio of a circle's circumference to its diameter, appears not just in every textbook but in the fundamental equations of general relativity and quantum mechanics. The mathematical constant E, the base of the natural logarithm, is found everywhere growth and decay are modeled, from population biology to the radioactive half-lives of elements. Their ubiquity suggests they are not human inventions but universal discoveries, part of the operating system's native language. The fact that these abstract mathematical entities are so deeply embedded in the physical behavior of the cosmos points to a reality where mathematics and physics are not just describing the universe, they are inseparable from it. The universe is quite literally made of math. This profound connection led pioneering physicists like Arthur Eddington to a near mystical fascination with these numbers. Eddington, who led the expedition that first confirmed Einstein's theory of relativity, became convinced that these constants were the key to a final, unified theory. He spent years attempting to derive their values from pure logic and numerological relationships, believing that their precise values were not accidental but necessary and meaningful. While his specific methods are not part of modern physics, his core intuition that these numbers are profound clues to a deeper truth continues to resonate. They are the fixed points in the swirling complexity of physical law, the immutable signatures that any complete theory of everything must ultimately explain. The staggering improbability of so many independent constants all landing on the exact values needed for a complex, life-permitting universe is what elevates this from a curiosity to a powerful anomaly. It feels less like a series of lucky breaks and more like the careful calibration of a master craftsman. The numerical harmony we observe is the reason we can do physics at all. It is the consistency that allows us to predict eclipses thousands of years in advance and to send probes to the outer planets with pinpoint accuracy. This reliability suggests a cosmos built on a foundation of rational, consistent principles, a universe that is not just orderly but intelligibly so. It is this very intelligibility that allows us to decode its patterns, leading us to suspect that the patterns themselves are the product of a deeper intelligence. This mathematical elegance finds its most beautiful and powerful expression in a concept that is both a tool and a truth, the principle of symmetry. This deep-seated love for balance and pattern is written into the very laws that govern reality. If the numerical constants are the fixed settings of the cosmos, then symmetry is the elegant principle that organizes them into a coherent and beautiful whole. At its heart, a symmetry in physics is a change that leaves something looking the same. Rotate a perfect sphere by any amount and it remains unchanged. That rotational symmetry is a clue to its underlying perfection. physicists have discovered that these symmetries are not just aesthetic preferences. They are the fundamental source of the universe's stability and the very reason we have laws of conservation. This profound connection was crystallized in a groundbreaking theorem by the brilliant mathematician Emmy Noether. She proved that for every continuous symmetry in nature, there is a corresponding conserved quantity. The fact that the laws of physics are the same everywhere, a symmetry of translation in space, leads directly to the conservation of momentum. The fact that those laws are the same at every moment in time, a symmetry of translation in time, gives us the conservation of energy. This means the stability of our entire reality, the predictability that allows a planet to orbit a star for billions of years, is underwritten by these hidden, beautiful symmetries. The greatest triumph of this principle is the Standard Model of particle physics, a framework that describes the fundamental building blocks of matter and the forces through which they interact. The entire elaborate structure of the Standard Model is built upon a tapestry of abstract symmetries known as gauge symmetries. These are not simple rotations in space, but more complex, internal symmetries that dictate how particles like electrons and quarks can interact with force-carrying particles like photons and gluons. It is this symmetrical foundation that makes the model so powerful and predictive. The symmetries act as strict rules that the particles must obey, ensuring that interactions happen in specific, consistent ways. Without this underlying symmetry, the universe would be a chaotic soup of unpredictable interactions. With it, we have a cosmos of stunning order and reliability. But a universe of perfect, unbroken symmetry would also be a universe of utter boredom. If all symmetries remained perfectly intact, every particle would be massless and zip around at the speed of light. There would be no atoms, no chemistry, no stars, and no us. The incredible creativity of the cosmos arises from a delicate and beautiful dance between symmetry and its breaking. This is where the Higgs mechanism comes into play. Think of it like a crowded dinner party. Initially, the room is perfectly symmetrical, every seat is the same, and every guest is free to mingle equally. But then, an influential celebrity enters the room. Suddenly, the symmetry is broken. Guests now cluster around this one charismatic figure, and the even distribution of people is lost. In the cosmic analogy, the entire universe is once filled with a perfectly symmetrical field, the Higgs field. But as the newborn universe cooled, this field underwent a phase transition. It acquired a non-zero value everywhere, breaking the original symmetry. This breaking is what gives mass to fundamental particles like electrons and quarks. The particles that interact strongly with the Higgs field are slowed down, acquiring mass, while those that don't, like photons, remain massless and fast. This broken symmetry is the reason for the incredible diversity of matter in the universe. It is the cosmic mechanism that allows for structure and complexity to emerge from a bland, symmetric beginning. This interplay has led visionary physicists like Frank Wilczek to describe the universe not as a machine, but as a work of art. The symmetries are the underlying compositional principles, the golden ratios and harmonic rules that the cosmos uses to create. The broken symmetries are the artist's improvisations, the moments of creative departure that introduce variation, interest, and form. The universe is both a masterpiece of order and a hotbed of creative innovation, all governed by these profound mathematical principles. This artistic elegance hints at an intelligence that expresses itself not through rigid control, but through a beautiful balance of constraint and freedom. The laws are tight enough to provide stability and predictability, yet flexible enough to allow for the spontaneous emergence of galaxies, life, and consciousness. It suggests a cosmos that is both knowable and endlessly surprising, a system that invites exploration because it was built on a foundation of exquisite, intelligible beauty. This seamless blend of rigid law and creative potential naturally makes one wonder if the entire cosmic process might be a form of computation, with the universe itself acting as the ultimate computer. This breathtaking view of the cosmos as a symphony of symmetry and its creative breaking brings us to a theory that takes this idea of an intelligible, computational universe to its logical extreme. What if the universe isn't just like a computer in a metaphorical sense, but actually is one, operating on the most fundamental level possible? This is the provocative proposal of the quantum computation universe theory, an idea championed by visionary physicists like Seth Lloyd at the Massachusetts Institute of Technology. He doesn't suggest that the universe is a digital computer made of silicon chips, but rather that it is a quantum computer of unimaginable scale, with every particle, every photon, and every ripple in spacetime acting as a component in a vast, ongoing cosmic calculation. To grasp this, we need to understand what a quantum computer is. Unlike a classical computer, which processes bits that are either a 0 or a 1, a quantum computer uses quantum bits or qubits. A qubit can be a 0, a 1, or both at the same time, a state known as superposition. This allows a quantum computer to perform a staggering number of calculations simultaneously, exploring countless possibilities in parallel. Now apply this concept to the fabric of reality itself. In this view, every elementary particle is a qubit. Its properties, position, momentum, spin, are not fixed until they interact with something else, much like a qubit's value isn't fixed until it's measured. The entire universe is a seething network of these qubits, constantly interacting, entangling, and processing information. The laws of physics, from gravity to electromagnetism, are not arbitrary rules but the algorithms that govern how these qubits interact and evolve. The unfolding of time is simply the processing of these algorithms one step at a time. This transforms our understanding of what we perceive as empty space. Quantum vacuum is not a true void. It is a frenetic foam of virtual particles flickering in and out of existence, a phenomenon we know as quantum fluctuation. From the perspective of the universe as a quantum computer, this isn't random noise. This is the cosmic processor running its background calculations. The vacuum is buzzing with computation. Every cubic centimeter of empty space is constantly performing operations, flipping bits, and processing the information that defines reality. This means the universe is not a static stage. It is a dynamic cognitive system. It is thinking, calculating, and manifesting its own reality through a process of continuous information exchange. This perspective elegantly bridges the chasm between the two great pillars of 20th century physics, general relativity and quantum mechanics. General relativity beautifully describes the universe on the large scale, the warping of spacetime, the dance of galaxies using the language of geometry. Quantum mechanics describes the bizarre, probabilistic world of the very small using the language of wave functions and probabilities. The quantum computational view offers a potential common language, information. Both gravity and quantum behavior could be seen as emergent properties of a deeper, information-theoretic reality. Spacetime itself might be a network of entangled qubits, with gravity arising from the way information is stored and processed across that network. What does this mean for the anomalies we've been exploring? If the universe is a computational system, then the fine-tuning of physical constants could be seen as the initial settings or the fundamental parameters of the cosmic operating system. The strange patterns in the cosmic microwave background might be the visual output of the universe's first foundational calculations. Even phenomena like quantum entanglement, where particles remain connected across vast distances, makes perfect sense. They are simply qubits that are still part of the same processing operation, their information forever linked. This view doesn't necessarily eliminate the need for a programmer, but it reframes the question. The intelligence behind the cosmos might be less of a watchmaker and more of a software architect who designed the initial algorithms and set the system running. Or perhaps the universe is a self-programming, self-organizing system, and the intelligence is an emergent property of the computation itself, a cosmic mind awakening as it computes. This incredible idea that the universe is not just a place, but a process of cognition, naturally leads us to consider the most intimate and controversial anomaly of all: the potential for consciousness to directly influence this cosmic computation. But if the universe is indeed a vast, interconnected quantum computer, where information is fundamental and everything is linked, then it forces us to confront the most intimate and controversial mystery of all: the nature of our own consciousness within this system. We arrive at an anomaly that has been relegated to the fringes of science for decades, not because the evidence is absent, but because it challenges the very core of our materialist worldview. This is the perplexing realm of psychic phenomena, reports of telepathy, precognition, and remote viewing that suggest the human mind might not be locked inside the skull, but could be interacting with the cosmos in ways that defy our current understanding of space and time. The concept of telepathy, the direct transmission of thoughts or feelings between individuals, is an ancient one found in folklore and spiritual traditions across the globe. For modern science, it has long been considered impossible, a violation of the laws of physics as we know them. After all, how could a thought generated by the neural activity in one brain possibly influence another brain across a room or across the world without any known physical signal? It seems to require some form of energy or connection that we cannot measure. Yet, this is precisely where the quantum view of the universe offers a potential, albeit speculative, framework. If quantum entanglement demonstrates that particles can be instantaneously connected regardless of distance, then perhaps consciousness, if it is in some way rooted in or interacting with these quantum processes, could also exhibit non-local properties. The mind might not be generating these connections, but rather tapping into a pre-existing, deeply interconnected reality, a cosmic network where separation is an illusion. To move beyond anecdote and into the realm of data, researchers have designed rigorous experiments to test these ideas. One of the most common is the Ganzfeld experiment, a procedure designed to test for telepathy under controlled conditions. A receiver is placed in a state of relaxed sensory deprivation, often with halved ping-pong balls over their eyes listening to white noise, to quiet the normal chatter of the brain. In a separate, isolated room, a sender is shown a randomly selected image or video and is asked to mentally transmit that content to the receiver. The receiver is then shown 4 possible options and asked to select which one they believe was being sent. By pure chance, we would expect a hit rate of 25%. But across hundreds of these studies, meta-analyzers have consistently shown a small but statistically significant deviation above chance, hovering around 32%. This extra 7% may seem tiny, but over thousands of trials, the odds of it being a random fluke become astronomically low. This is where researchers like Dean Radin, chief scientist at the Institute of Noetic Sciences, enter the picture. For decades, Radin and his colleagues have been compiling this evidence, conducting their own tightly controlled experiments and analyzing the work of others. Their conclusion is not that psychic powers are a superhuman ability, but that these phenomena point to a fundamental interconnection between mind and world. Radin proposes that consciousness might be a field-like phenomenon, not unlike a gravitational or electromagnetic field, that is fundamental to the universe rather than a product of it. In this view, the brain is not a generator of consciousness but a receiver or transducer, filtering a vast, non-local consciousness into our individual, personal experience. This would mean that intelligence and awareness are not confined to biological organisms, but are inherent properties of the cosmos itself, with space itself acting as the medium through which mental phenomena can occur. Perhaps even more baffling than telepathy is the concept of precognition, or the ability to perceive future events. This strikes at the heart of our linear experience of time. If valid, it suggests that the arrow of time is not as absolute as it seems, and that information can, in some circumstances, flow backward from the future to the present. Experiments in this area often measure unconscious physiological responses. In one famous series of studies, participants were shown a series of images on a computer screen. Most were calm, neutral pictures, but a random few were highly emotional or violent. Sensors attached to the participants measured subtle changes in their skin conductance, heart rate, and brain activity. The astonishing result was that participants' bodies would often react significantly before the disturbing image was randomly selected and shown on the screen, as if their unconscious mind was anticipating the upcoming emotional event. This presentiment effect has been replicated in multiple labs, suggesting that our bodies might have a faint, intuitive connection to events that haven't yet happened in our local timeline. The implications of this are nothing short of revolutionary. If consciousness can operate outside the bounds of space and time, it challenges the materialist view that the physical world is the primary reality, and that mind is merely a secondary illusion. Instead, it opens the door to a participatory cosmos where mind and matter are deeply intertwined, where thought might not just observe reality but could potentially influence it. This idea that consciousness could be a fundamental force in the universe provides a startling new lens through which to view our final anomalies. It suggests that the strange, physics-defying objects sometimes seen in our skies might not just be nuts and bolts spacecraft from another planet, but something far more complex and mysterious, potentially intertwined with the very consciousness that is trying to observe them. For centuries, reports of strange lights in the sky were dismissed as folklore, fantasy, or the misidentification of mundane objects. Pilots who spoke of incredible craft were often grounded, their careers jeopardized by the stigma. But in a stunning reversal, the conversation has now shifted from the fringes to the highest levels of government and military authority. What were once called UFOs, or unidentified flying objects, are now more formally designated as UAPs, unidentified aerial phenomena. This change in terminology is crucial. It moves the discussion away from the loaded idea of flying saucers and toward a neutral, data-driven investigation of mysteries that pose a genuine national security concern and a profound scientific puzzle. The U.S. Department of Defense's release of declassified videos, such as the now famous Tic Tac incident from 2004, has provided the public with a glimpse into this enigmatic world. In that event, U.S. Navy pilots from the Nimitz Carrier Strike Group encountered a smooth, white, oblong object about 40 feet long with no visible wings, engines, or exhaust plumes. This craft performed maneuvers that defy our current understanding of physics. It was tracked on multiple advanced sensor systems, including radar and targeting pods, and witnessed by highly trained pilots. The object dropped from an altitude of over 80,000 feet to just 50 feet above the ocean in less than a second, a velocity and acceleration that would generate G-forces capable of tearing any known material or biological organism apart. Even more astonishingly, it then transitioned seamlessly from the air into the water, a trans-medium travel capability far beyond any technology we possess. This is not an isolated case. The preponderance of evidence from these military encounters points to 5 observables: anti-gravity lift, instantaneous acceleration, hypersonic velocities, low observability or cloaking, and trans-medium travel. These are not simply fast airplanes. They represent a mastery of physics that appears to bypass inertia and aerodynamic principles altogether. They operate without sonic booms, without heat signatures consistent with propulsion, and with a control of energy that seems to violate the conservation laws we hold as fundamental. When such performances are recorded by the world's most sophisticated sensor technology and reported by our most credible observers, they can no longer be easily dismissed. They demand a rigorous scientific investigation, which is precisely what initiatives like the U.S. government's All-Domain Anomaly Resolution Office are now tasked with undertaking. While the vast majority of UAP reports will inevitably have conventional explanations, whether balloons, military tests, atmospheric phenomena, or simple misidentifications, it is the stubborn remaining percentage, perhaps 5 to 10%, that constitutes a genuine anomaly. For these cases, the extraterrestrial hypothesis is often the first and most intuitive explanation. The idea that these objects are probes or craft from another civilization, perhaps monitoring our planet, is a compelling narrative. However, some of the most insightful researchers in the field, like the computer scientist and astronomer Jacques Vallée, argue that the phenomenon may be far stranger and more complex than simple interstellar visitation. Vallée, who served as the model for the French scientist in Steven Spielberg's Close Encounters of the Third Kind, points to the long, bizarre history of the phenomenon, which often includes elements that seem more psychological or symbolic than physical. Reports throughout history describe interactions with beings, messages of environmental warning, and objects that seem to manipulate human perception itself. Vallée proposes that UAPs might not be from a distant star, but could be interdimensional, originating from a reality coexisting with our own but operating under different physical laws. Even more radically, he and others have suggested these phenomena might be intrinsically tied to consciousness, appearing in forms that our minds can interpret, perhaps as a way to communicate or even as a manifestation of a collective human psyche interacting with the fabric of reality. In this view, the craft are not nuts and bolts machines, but something more akin to avatars or projections, temporary interfaces with an intelligence that is utterly alien in the truest sense of the word. This anomaly, therefore, is not just about objects in the sky. It is a challenge to our entire framework of reality. The behaviors exhibited by these UAPs suggest a physics that is either vastly more advanced than our own or operates on principles we have not yet begun to comprehend. They could be literal hardware from another world, or they could be glimpses of a deeper layer of a coded reality, where the lines between the physical and the mental, the material and the conscious, are not as distinct as we believe. They urge a profound humility, reminding us that our current scientific model is incomplete. To dismiss them is to close a door on potentially the greatest discovery in human history. To investigate them with an open but critical mind is to acknowledge that the cosmos is filled with mysteries that may force us to rewrite the textbooks of physics, biology, and consciousness itself. This incredible possibility that we are not alone and that reality is far more malleable than we thought naturally leads us to re-examine our very place in the cosmos through the lens of a principle that places us at the center of the universe's conditions. The multiverse theory emerges as a breathtakingly ambitious attempt to solve the puzzle of our universe's perfect fine-tuning. Imagine not just one cosmos, but an infinite, bubbling foam of universes, each born with its own unique, random set of physical constants and laws. In this vast cosmic lottery, most universes would be stillborn or barren, collapsing instantly, flying apart too fast for atoms to form, or simply existing as empty, featureless voids. But in an infinite ensemble, every possibility, no matter how improbable, must eventually be realized. We find ourselves in this particular universe, with its gravity just right and its nuclear forces perfectly balanced, not because it was chosen or designed, but simply because it is one of the rare ones that could support conscious life. This is the anthropic principle applied on a gargantuan scale. We observe a universe compatible with our existence because we couldn't possibly observe one that isn't. It's a cosmic version of the observation that a puddle of water is perfectly shaped to fit the hole it finds itself in. This idea, often called the anthropic selection effect, offers a powerful and elegant escape from the need for a single, finely tuned universe. It transforms the question from "why is our universe so perfect?" to "what are the statistical rules that govern the multiverse?" Prominent physicists like Max Tegmark and the late Stephen Hawking found this a compelling answer, a way to explain the appearance of design without invoking a designer. It suggests that the incredible improbability of our existence is an illusion, a trick of perspective. Of course, we see a universe that looks designed for us. We are the selectors, the living, breathing products of its specific, life-allowing rules. In this view, the cosmos isn't encoded with intelligence. It's a vast, mindless generator of possibilities, and we are simply the lucky winners of the ultimate existential jackpot. Yet, for all its explanatory power, the multiverse theory simply pushes the mystery back one step, raising even deeper and more profound questions. If there is a multiverse, what is the mechanism that generates it? The leading candidate is the theory of eternal inflation, where the fabric of spacetime is constantly bubbling with new universes. But this process itself requires a very specific set of initial conditions and laws to operate. Why does this meta-reality, this universe-generating engine, exist at all? And why does it operate according to consistent, mathematical rules that allow for the production of stable universes in the first place? We are left wondering why there is something rather than nothing, and why that something follows any rules whatsoever. The existence of a law like multiverse seems to require its own form of fine-tuning, suggesting that the problem of cosmic order hasn't been solved, but merely relocated to a higher level. This leads some thinkers to propose that the multiverse itself might be part of an intelligently structured system. Perhaps the laws that govern the creation of new universes are not random, but are themselves finely tuned to produce a rich diversity of cosmic environments, including some that can harbor life and consciousness. This idea of a meta-intelligence, or a universe of universes with its own inherent design principles, is a staggering one. It expands the notion of an encoded cosmos to a truly cosmic scale, suggesting that the intelligence we sense might not be programming a single universe, but an entire fractal ensemble of them. Our universe's laws would then be a local manifestation of a deeper, more fundamental code that governs the entire multiversal structure. Therefore, the multiverse is a double-edged sword. On one hand, it provides a powerful naturalistic explanation for fine-tuning, dissolving the need for a single creator. On the other, it opens up a Pandora's box of even grander metaphysical questions about the ultimate origin of reality and the apparent deeply rooted order that permeates all of existence. It challenges us to see our home not as a solitary accident, but as one thread in an impossibly vast and possibly intelligently woven tapestry of realities. This expansion of our cosmic perspective makes the fabric of existence seem even more mysterious, setting the stage for an anomaly that challenges the very linearity of that existence. Of all the cosmic rules we take for granted, the linear flow of time feels the most absolute. We remember the past, we experience the present, and we anticipate the future in a one-way procession that seems as fundamental as gravity itself. Yet, buried within our most successful theory of gravity, Einstein's general relativity, are solutions to the equations that suggest this linearity might be an illusion, a local condition rather than a universal law. These solutions are known as closed time-like curves, and they are the theoretical foundation for time travel within the fabric of spacetime itself. A closed time-like curve is precisely what it sounds like, a path through the universe that, if you were to follow it, would bring you back to your own past. It's not a metaphor, it's a potential feature of the cosmic landscape under extreme conditions, like those near the immense gravitational whirlpools of rotating black holes or in the presence of exotic matter with negative energy density. The mathematics doesn't forbid it, it simply opens a door to a universe where cause and effect, the very bedrock of reality, become terrifyingly malleable. This possibility immediately conjures up the famous paradoxes that have fueled science fiction for generations. The grandfather paradox is the most chilling. What if you traveled back in time and prevented your own grandfather from meeting your grandmother? Would you simply cease to exist, creating a logical inconsistency that unravels reality? Another is the ontological paradox, where an object or piece of information is sent back in time with no origin. Imagine giving the schematics for a time machine to your past self, who originally designed it. These aren't just fun brain teasers, they are serious philosophical and physical problems that challenge our understanding of existence, information, and free will. They suggest that if time travel is possible, then the universe must have a built-in mechanism to prevent such logical inconsistencies from occurring, a kind of cosmic error correction protocol. This is where the work of physicists like Kip Thorne and his colleagues becomes so fascinating. When they delved into the mathematics of these closed time-like curves, they discovered something remarkable. The equations seem to impose what they call consistency conditions. In any scenario involving a time loop, the events must always be self-consistent. The mathematics simply will not allow a paradox to happen. In the case of the grandfather paradox, this might mean that your actions in the past would be somehow prevented. The gun would jam, you would miss, or some unforeseen event would always intervene to ensure the timeline that produced you remains intact. The universe, in this view, would operate like a self-correcting computational system. The initial conditions and the laws of physics would work in concert to compute only those histories that are consistent from start to finish, with any potential paradoxes resolved before they can ever arise. This computational analogy is incredibly powerful. It suggests that time itself might not be a passive stage but an active processor of information. In this model, the past, present, and future might not be fixed in a block universe but could be in a state of dynamic negotiation, with information flowing not just forward but also backward in time. This idea is known as retrocausality, and while it remains highly speculative, it offers a way to interpret some of the deepest puzzles in quantum mechanics. For instance, in the delayed choice experiment, a decision made in the present about how to measure a particle seems to influence that particle's behavior in the past. If retrocausality is real, it wouldn't be magic. It would simply be a feature of how the universe processes events, with causes and effects being determined globally across the entire timeline rather than strictly locally and sequentially. The cosmos would be ensuring a consistent story, much like a writer going back to edit the first chapter to make it align perfectly with the final one. This perspective invites us to see time not as a river flowing in one direction, but as another dimension of cosmic intelligence, a complex, self-regulating system that maintains coherence across all of history. The potential for closed time-like curves and the consistency conditions they require hint at a universe that is fundamentally computational at its core, processing reality in a way that preserves meaning and avoids logical chaos. It transforms time from a simple arrow into a sophisticated mechanism, perhaps the most profound mechanism of all, for ensuring that the cosmos tells a story that makes sense from every point of view, from the beginning to the end and back again. This final anomaly brings our journey through the clues of an encoded cosmos to a close, not with a simple answer, but with a profound invitation to see every aspect of reality, even the flow of time itself, as part of a grand, intelligible, and perhaps even intelligent design. So where does this leave us after this incredible journey through 24 of the cosmos's deepest secrets? Each anomaly on its own is a fascinating puzzle that challenges the edges of our understanding. But when you step back and look at them together, a breathtaking pattern begins to emerge from the noise. It's a pattern that paints a picture of a universe that is anything but a cold, empty, and accidental void. Instead, we see a cosmos that is vibrant, interconnected, and seemingly rich with information, order, and perhaps even a whisper of intention. From the impossibly precise settings of the fundamental constants that let atoms form, to the quantum entanglement that connects particles across galaxies, to the large-scale cosmic web that mirrors a vast neural network, the evidence points toward a reality that is fundamentally structured and intelligible. This isn't about finding a single smoking gun. It's about the cumulative weight of all these mysteries, each one adding another thread to a tapestry that suggests something profound is going on. This grand synthesis doesn't force us into one narrow conclusion, but rather opens up a spectrum of incredible possibilities. One compelling interpretation is that the universe itself possesses a form of fundamental mind or consciousness. This isn't about a bearded man in the sky, but rather the idea that awareness could be a basic property of reality, as fundamental as space or time. In this view, the cosmos is a single, unified entity experiencing itself subjectively through countless individual perspectives through us. The laws of physics and the patterns we see are the grammar of this cosmic mind's thought process. Another equally mind-bending possibility is the simulation hypothesis, which reframes all these anomalies as features of an ultra-advanced reality engine. The fine-tuning is the initial parameter setting, the mathematical nature of physics is the underlying code, and quantum weirdness is the system optimizing its processing power. We might be living in a universe that is quite literally computed, and our search for meaning is an attempt to understand the programmers or the purpose of the simulation itself. A third path is to see these patterns as evidence of laws of nature. We have not yet discovered a deeper layer of physics where information is the primary currency and consciousness is an emergent property of complex systems. This doesn't require a creator or a program, but it does suggest a universe that is inherently self-organizing, trending toward complexity and consciousness as a natural outcome of its foundational principles. What's truly remarkable is that these different ideas, a conscious cosmos, a programmed reality, or a new physics of information, are not mutually exclusive. They can intersect and overlap in fascinating ways. A universe that is a simulation could be running on the hardware of a fundamental cosmic mind. A self-organizing universe trending toward consciousness might eventually create simulated worlds of its own. The common thread weaving through all these interpretations is the concept of a cosmic code. Whether it's the mathematical language of physics, the bit-like nature of quantum information, or the symbolic patterns in psychic phenomena, we keep finding evidence that reality is built upon a foundation of meaningful, structured information. This shifts our entire paradigm. We are not just insignificant specks on a random rock in a meaningless void. We are active participants in a cosmos that appears to be cognitive, participatory, and perhaps even communicative. We are embedded in a reality that seems to invite us to decode it, to understand it, and to engage with it. This perspective bestows upon humanity a role of tremendous responsibility and breathtaking potential. We are not just the universe's way of knowing itself, as Carl Sagan poetically said. We may be its way of growing, evolving, and perhaps even healing itself. This synthesized view of an encoded cosmos prepares us for our final, and most personal, step, to ask what all of this means for our future, and to decide how we will respond to this incredible invitation to wonder. And so we arrive here at the edge of the known, looking out into a cosmos that has revealed itself to be anything but silent and empty. Our journey through these 24 anomalies is more than just a list of strange facts. It's a fundamental shift in perspective. We began by peering into the vast darkness and have ended by contemplating a universe that might be shimmering with information, humming with computation, and perhaps even pulsing with a form of consciousness. This isn't a conclusion, but an invitation, a starting point for a new way of seeing everything. The greatest takeaway isn't a single answer, but the powerful collective weight of all these mysteries, pointing toward a reality that is deeply, profoundly intelligible. It suggests that the cosmos is not a random accident, but a realm of exquisite order, one that seems to invite us to listen, to learn, and to participate. Carl Sagan's timeless words remind us that the true engine of discovery is not certainty, but a fearless and joyful curiosity. The moment we think we have all the answers is the moment we stop truly looking. This exploration into the encoded cosmos is a celebration of the questions themselves. Why does mathematics, a product of the human mind, describe the universe with such uncanny accuracy? What is the nature of the connection that allows entangled particles to whisper to each other across light years? Does our own act of observation play a role in weaving the fabric of reality? These are not just puzzles for physicists in lab coats. They are deeply human questions about our place in a grand and mysterious story. Embracing the mystery means being comfortable with not knowing, while passionately believing that there is more to know. As we stand on this threshold, the tools for the next great leap are already in our hands. Our telescopes are growing more powerful. Our quantum computers are probing deeper into the fabric of information, and projects searching for extraterrestrial intelligence are scanning the skies with unprecedented sensitivity. The next decade may bring revelations we can scarcely imagine today. We might detect a biosignature on a distant exoplanet, finally receive a signal that is unambiguously artificial, or discover a new fundamental particle that opens a doorway to a deeper layer of reality. Each new piece of data is another character in the cosmic code, another line in the universe's story waiting to be read. The pace of discovery is accelerating, and with it, our understanding of this incredible reality we call home. This is why your curiosity matters. Every time you look up at the night sky with a sense of wonder, every time you share a fascinating article with a friend, every time you support scientific research and public outreach, you are contributing to this grand human project of understanding. We are all explorers in this endeavor. So I'm genuinely curious to know which of these anomalies resonated most deeply with you. Was it the eerie connection of quantum entanglement, the precise fine-tuning of the universe's constants, or the tantalizing possibility of the simulation hypothesis? Share your thoughts in the comments below. Let's continue this conversation and learn from each other's perspectives. If this journey through the mysteries of the cosmos has sparked your imagination, there's so much more to discover. Be sure to like this video if it made you think, and subscribe to the channel so you don't miss our next deep dive into the wonders of space, time, and consciousness. Hit the bell icon to get notified every time we upload new content. The universe is the greatest story ever told, and we're just beginning to turn the pages. Thank you for watching, and remember, wherever you are, keep looking up, keep asking questions, and never stop wondering at the magnificent, encoded cosmos we are so privileged to be